All right, let's go way back now and take a look at problems involving chapter 2. Chapter 2 was where we were looking at limits. We didn't know about derivatives yet. All right, so the first objective asks you to use a graph to determine if a limit exists, and if it doesn't exist, to try to explain why. So 25, 27, and 31 were problems you could look at. Thought we'd look at 31 together. All right. So on question number 31, we have this graph right here that we're looking at. So when they ask me to do f of 1, that's just the value of the function at 1. So I'm looking for an ordered pair that has an x of 1. I'm looking for this. What corresponds to an x coordinate of 1? Okay. And I can see that would be 2. Okay. So f of 1 would be 2. Now, on the next question, it asks me what's the limit of the function. And see, the function is this, all these ordered pairs you see, right? That's the function, okay? So it's asking me for the limit of that function as x approaches 1. And see, it's not 1 with a little minus sign after it or 1 with a plus sign. So it means that you're looking at the limit as you approach 1 from both sides. So when I come in from the right, and when I come in from the left, I don't hit the same, I'm not at the same height, right? When I come from the right, I get 1. When I come from the left, I get what appears to be maybe 3.5, right? So on this one, the limit as x approaches 1 does not exist because the limit as x approaches 1 from the right, okay, would equal what appears to be 1, while the limit as x approaches 1 from the left, from the negative side, looks like it's at, let me check that, looks like it's around 3.5. Big thing is, it looks like it's around, I'll say approximately. Big things is those don't match. The right and the left-sided limits don't match. So does not exist would be the answer to B. All right, then if I go over here and I look at f of 4, here's an x value of 4, and f of 4 doesn't exist. There's no ordered pair on this graph that has an x coordinate of 4. So f of 4 does not exist. Okay. And then when we're analyzing the limit as x approaches 4, the limit of the function f as x approaches 4 from the right or from the left, do you see how it hits the same height? They're both leading to that point, and that point has a height of 2. Your answer would be 2. Okay. All right, now the next objective is just asking you to get the limit of the function, no graph given to you. Okay, so this one you could do 7, 15, or 17. Why don't we go ahead and look at question, say, 15. Okay, so when you're evaluating limits, you really ought to try to do just direct substitution. Plug in 1 for x everywhere. And as long as you don't get anything undefined, you don't get like a 0 in a denominator or a negative under a radical, then that's a great way to do it. And we wind up with the answer being 1 over 1 plus 4, which would be 1/5, and we're done. Okay, you are going to have one that's that straightforward. So don't be thinking everything's got to be as hard as possible. All right, let's go ahead and take a look at section 2.3. On this one, we're gonna do one of these. Let's go ahead and do 51. All right, so I'm going to try to use direct substitution on that one also. I'm doing 51. So I wanted the limit as x approached -3 of this function, this rational function. All right, watch what happens though. When I plug in a -3, do you see how down here that -3, when it's squared, would be 9? So I'd get a 0 in the denominator. All right, so that means direct substitution isn't the way to do this one. That's not going to work. Okay, so I'm not going to do that. And that's the time when you have to have some technique for fixing the problem. When we did this the first time, sometimes you fixed it by factoring and then canceling out a common factor. Sometimes you had to rationalize the numerator or denominator. And sometimes, what was the third thing we had to do? Oh, sometimes you had to simplify a complex fraction. So this is a factoring situation. Maybe factoring would help us. So see how I can break up the denominator into x minus 3, x plus 3. Then the numerator I could factor into x and x with a 3 and a 2. And I want the middle term to be plus x. So I'm going to put a plus on the bigger of the two numbers, a minus on the smaller. Always FOIL that back out. Make sure you didn't mess up your factoring. All right. So when I'm looking at that, I know that this rational function would have the same limit as x approaches -3 as this one. Like I could knock out that trouble spot right there. That's actually going to be where at x equals -3, there's just going to be a hole, okay? Because it was removable. You could knock it out. All right, so once I've transformed the original rational function into something that's equivalent except for right at -3, right at one spot, then I'm able to use direct substitution at this point and plug in. And I get a -5 over a -6. And so my final answer would be positive 5/6 on that one. All right, so remember, if direct substitution doesn't work, you may have to factor, okay? And see if you can cancel out a common factor. And that kind of leads into, let me see, nope, not that one. All right, to the next issue, where they're asking you to identify values of x where the function is not continuous, and then talk about whether they're removable or non-removable. All right, and they said look at 41, 45, and 47. So why don't we take a look at 47? Okay, so on 47, I would look at the denominator because that's where trouble spots come from, because you can't divide by 0. I would factor it. And x squared minus 3x minus 10, I'm assuming one of these is going to be a 2 because of what's in the numerator. So that's going to be my first try. I need it to be negative in the middle here, right here. So I'm going to make it minus on the 5, plus on the 2. And I like that because that x plus 2 on top and bottom makes for an interesting question. So there's two trouble spots, 2 points of discontinuity, 2 places where the function is not continuous. Okay. One is at x equal 5. The other one is at x equals -2. All right. They want us to talk about, so those are the 2 places where f is not continuous. And then we got to label them as removable or non-removable. Well, see that x plus 2 factor I could cancel out to get a function that is mostly equivalent to what I had originally, except for at -2. All right, so I was able to cross out the x plus 2 factor. So the value associated with that factor, that's going to be a place where you're just going to have a hole rather than a vertical asymptote. It's going to be a situation like, well, let's see, I can pretty much tell. Well, it's going to be a situation where you have like a hole, not a vertical asymptote type of discontinuity. So that's a removable type. The factor was, that trouble spot was able to be canceled out because of the fact you had a common factor. But at 5, you're going to have a vertical asymptote. Okay, you can't remove the problem. Okay, so that's a discontinuity that's kind of a bad one. So that's a non-removable discontinuity. Okay, all right, let's take a look at one more thing from chapter 2 material. It also had to do with limits, but they're one-sided limits. All right, so why don't we do a couple of those? Why don't we look at 39 and then maybe look at 40? Okay, so on 39, we're being asked to find the limit, remember the notation, as x approaches a negative 3 from the left, from the negative side. Okay, all right, so the first thing I might do is think about plugging in a negative 3 in general. All right, when I do that on top, I get a 0 on top. When I do that on the bottom, I'd get a 9, and then minus 3 minus 6, I'd get a 0 on the bottom. That means I have an indeterminate form. Okay, so that's a problem just like it was on an earlier one. If direct substitution doesn't work, I'm going to try some of those techniques. Factoring was one of them, rationalizing numerators, simplifying complex fractions. So this is a factoring one to try. So when I do, I get an x and an x, a 3 and a 2, with a plus on the 3 and a minus on the 2. I foiled it back out and checked it. That works. So originally I tried to plug in negative 3, but I got a 0 in the denominator. Now I noticed that the denominator can be factored, so I can knock that factor out, and the original limit would be equivalent to the limit of this new rational function I just created, which can now be evaluated by just plugging in using direct substitution, and whether you came from the left or the right really didn't matter, and I wind up with a negative 1/5. Okay. All right, now what's going to be harder on number 40 is just the factoring is harder. I thought we'd go ahead and look at it too. Here we wanted the limit as x approached a negative 1/2 from the right. Okay, so first thing you might check, and you're doing that for 6x squared plus x minus 1, and then down here 4x squared minus 4x minus 3. So I'm going to think about that negative 1/2 going in there. I would get 4, negative 1/2 times itself would be 1/4, minus 4 times a negative 1/2 minus 3. So this would be 1 plus 2 minus 3. And there's that trouble spot, that 0 in the denominator. Okay, so let's try factoring. We'll see if we can get rid of that trouble spot and then just use direct substitution. So on this one, it's not an easy factoring problem. I'm not really sure how to factor it. I didn't try to do these ahead of time. So I would probably try to start with maybe a 2x and a 2x, because I usually do that when it's a perfect square. Okay, then because those two multiply to be 4x squared, these two have to be 3. So the only way to do that is a 1 and a 3. So let me just put in a 1 and a 3. Once they're in there, then I look at it trying to get my signs to work. Okay, this is going to work. I can put a negative on the 3 and a positive on the 1. And then when I FOIL out, I'll get 4x squared minus 6x plus 2x minus 3. If you're not a great factorer, please be sure to double check your factoring and make sure you have the signs correct. So that's how the bottom part factors. Okay, that works. Now that gives you a huge hint as to what's going to happen on top, because I'm hoping something's going to cancel out. So I'm imagining this to be a 2x and a 3x so that I get a 2x on top. Also, this negative 1/2 would cause this factor to be 0. So my first attempt is going to be 2x squared plus 1, and then 3x with a 1, and that would need to be a minus to get a negative 1. And then I FOIL it back out, and sure enough, that works. Okay, so now the original limit is equal to the limit as x approaches negative 1/2 from the right of 3x minus 1 over 2x minus 3. I was able to knock out that removable discontinuity. Now I'm going to try direct substitution. Doesn't really matter whether it's from the right or the left. In this case, I'm just going to plug it in because it doesn't give me a trouble spot. And I get a negative 3/2 minus 1, negative 3/2 minus 2/2. That's negative 5/2. Then I get a negative 1 minus 3, which is negative 4. I don't like the look of that, so I'm going to clean it up. Multiply by 2, and a negative divided by a negative is positive. So I'm going to come up with 5/8 for my final answer on number 40. Okay. So finding one-sided limits, but really it works the same as finding two-sided limits, unless it's some of those interesting ones that are approaching, you know, a different thing from the right as from the left. Okay. Oh, and that was the last one. That's all from chapter 2. So that's it for chapter 2.